onto discrete random variables. Okay, for the rest of the course, we're going to move away from the abstract framework of probability and focus on modeling scenarios that involve random numbers. So rather than starting with cards or dice or letters or animals, we're going to just work with random numbers, okay? And mainly what I mean by that is that even if we care about cards or letters or animals or so on, we're going to represent them with numbers and just keep in mind that they originally came from something else. The reason for doing this is it opens the door to more powerful techniques that we can use, and it'll allow us to explicitly model dependencies between random numbers in a way that we can think about it and reason about it more clearly. Okay, we'll see a lot more about this as we go along, but for now, let's just introduce the definition for a random variable. A random variable, which we denote with capital letters, in this case x, but you might also see y, z, w, and so on, but capital letter for random variable is a function that maps outcomes from the sample space to real numbers. So it's x, which is a function that takes the sample space big omega to the real line. And we also have the property that for any interval AB, the set of outcomes that get mapped between A and B, that is a valid event. Okay, so it belongs to the event space. Visually, I have my, let's say, 4 outcomes that I'm going to draw in this sample space, and I'm just going to map them onto the real line. Here's the real line. So let's say omega 1 is going to go to this point x1, right, which is positive. Omega 2 goes to x3. And this is just to point out that it doesn't have to go to its own unique number. So omega 2 in this case goes to x3, which is a negative number. And you'll see that omega 3 goes to x2, and so does omega 4. This whole thing is the mapping x, the random variable. So it carried the outcomes onto the real line. And it doesn't have to do it in any particular way. I could map all of the outcomes to a single number. Not very interesting, but I could do it. I could map them to unique numbers. I could map some of them to unique numbers, others not. Whatever I like. Okay, we're usually going to denote random variables, like I said, using uppercase letters from the end of the alphabet. So things like X, Y, and Z. And we'll usually use the beginning of the alphabet like A, B, and C for events. So we usually denote specific values that a random variable could take. So fixed values rather than the random aspect of it. We're going to use a lowercase letter. So we're going to use little x, little y, and little z to denote a arbitrary value. And the range, r sub x, is just going to be the range of the function x. Okay, so the random variable, we're going to call it discrete if the range is countable. Okay, meaning that I can index the set which consists of the range. So the range, I can index it with the natural numbers. So if it's finite, or something like the integers, it's definitely countable, and then I can say it's a discrete random variable. The experiment is where the randomness is actually coming from. Okay, so remember we had this set up in the beginning of the course where we had experiments that we observed. That's where the randomness comes from, and x is just a function of these random outcomes. However, it's very useful for our intuition to kind of forget about this and to start thinking about x as a random number on its own. Okay, so you can think about x as a random object, even though it's a function of a random experiment, it's helpful for us along the way to just think about it as a random number. Okay, so that's maybe a good way to start forming some intuition. Let's do some examples. So experiment 1, let's say I count the number of photons that hit a CCD pixel, right, in 1 millisecond. So the sample space in this case, it's going to be maybe 0 photons or 1 or 2, and just going on, all right? What's my random variable? In this case, my random variable is a function of omega, and it's just omega. So the experiment is to count the number of photons, and the random variable in that case is exactly the number of photons. The range is the same as the sample space in this case. So here, x is the same as the outcome, which is completely fine. So the mapping didn't change anything, and since this is a countable range, it's a discrete random variable, right? Okay. Second experiment. So let's say what I'm now going to do is I'm going to measure for this same kind of setup. Let's say I measure the exact time in milliseconds, okay, including decimals, between the arrival of the first and second photon at this CCD pixel, right? So maybe I get my first photon, and now I count how many milliseconds it takes to get the second photon. So the sample space is between 0 and infinity, including 0. And again, my random variable is just omega, and the range is the same as the sample space. Okay, so x is the same as the outcome here. So I had an experiment, and I just decided that the random variable is the same as the outcome. But it's not a discrete random variable, right? Because it comes from this continuum of uncountable outcomes. And this is kind of outside of our scope for now. So we're going to see how to deal with these kinds of random variables in the next chapter or unit. So for now, we're just going to set this aside. Okay, moving on. Let's now say what we're going to do is roll 2 four-sided die. Okay, so I'm going to roll them. And so we've done this before. And in that case, what we had is a sample space, which is the set of pairs ij. And we said that the ij can take values from 1, 2, 3, and 4. Okay, so in this setting, we're going to say that I'm only interested in the sum of the rolls. And here, x is not going to be the same as the outcome. I'm going to write x as I plus j, right? So the sum of the rolls. And the range is going to be, let's think about this for a second. So what is the lowest number I can get in the range? That's when I is 1 and j is 1. So I get 1 plus 1 is 2. And I get 3, 4, 5, 6, 7, and 8. And is this the last number in the range? Yes, because 4 plus 4 is 8. So that's the highest number I can get. Okay, so here x was a function of the outcome. So it was a little bit more interesting as a random variable. And it's still discrete because I have a finite list for my range. All right, so let's do yet another experiment, which is going to motivate some of the things we'll do later on. So let's say I have experiment 4, and I'm going to keep the same setup. So same setup that we just had with 2 four-sided die. And I'm going to define x in the same way, the sum of the rolls. Y is the square of x. Okay, what's the range of y? Well, I just look at the range of x and just square every term. So I get 4, 9, 16, 25, 36, 49, and 64. Okay, so the first thing to note is that y is a function of the random variable x. So what is going on with that? Well, if you think about it, this is fine because what is a function of a function? It's just a function. So this is itself a random variable. It's just that I've composed 2 functions together to go from the sample space to y. Okay, so it is also a random variable. Is it discrete? Yes, because the range is a finite list. Okay, that's it. We're going to do one more example, a little bit longer and maybe a little bit closer to the things that you're used to dealing with. So let's say our experiment is to ask a student about their letter grade in a class, okay, and they're willing to answer you. And to make things simple so we don't have to write down too many things, let's say that the only possibilities are A, B, C, D, and F. Okay, so no pluses and minuses. And now, the way I'm going to map this to a random variable is I'm going to use grade points. Okay, so I'm going to assign x omega to be 4 when it's an A, 3 when it's a B, 2 when it's a C, 1 when it's a D, and 0 when it's an F. Okay, so the range in this case is just going to be 0 through 4. Okay, so why do something like this? Well, x here is mapping letters to real numbers. Why would I do that? It's useful for computing things like grade point averages. Okay, so when I'm talking about my grade point average, I don't say that I have an A-B-ish average. I might say I have something like a 3.5, right? Because in that case, I averaged together some numbers. I did not average together letters. So this mapping from letters to numbers is enabling us to do things that are a little more interesting, like averaging. Okay, again, x is a discrete random variable. The range is a finite list. And let's just visualize finally what this looks like in terms of a mapping so we can get something a bit more concrete. So here I'm going to have in my abstract sample space my A, my B, my C, my D, and my F. And they're just floating around in this sample space universe. And now what I want to do in order to start doing some more interesting things is I'm going to draw the real line. In this case, the only parts of the real line I'm going to use are 0, 1, 2, 3, and 4. So that's going to be my x. And as we just discussed, I'm going to map each of these elements of the sample space onto a number. So a to 4, b to 3, c to 2, d to 1, and come on, f to 0, and then d finally making it to 1, squeezing in there. Okay, so that is a concrete example of something that you probably have done on your own, thinking about what letter grades correspond to in terms of grade points. And there's a good reason for doing that, because then you can compute an average. Okay, let's build up more of a framework for dealing with these scenarios. And to do that, we're going to introduce this idea of a probability mass function, abbreviated as a PMF. So the probability mass function, which we're going to denote by this P sub big X, little x. Okay, so this is a big P. It doesn't have two lines like the probability measure. It's just a capital P. It has a subscript, which is a capital X, and it has an argument, which is a little x. Okay, and it maybe takes a little getting used to, but I'm just spelling it out so that we all recognize those components. So this is a function, and what it does is it takes in an input, which is a possible value from the range. Okay, so it's a possible value of the random variable capital X, and the output of this function is just going to be the probability that X actually takes this value. Okay, that's what I'm actually interested in. So how do I work this out? So I have this PMF, and what I'm trying to get in here is the probability that the outcome actually maps to this little x. Okay, so I take the outcomes, I pass them through the random variable, and I see which ones are equal to the little x. I collect the set of all those things, and I pass it into the probability measure. Sounds complicated, but it's a thing that I can do, all right? So that's what this PMF represents. It's capturing the probability of these objects. Usually it's kind of annoying to write things in this format, and we're going to very quickly get used to dealing with PMFs and random variables. So we're going to usually just use a shorter way of writing this. So maybe I write just P for the set of the big X, so random variables that are equal to this little x. And implicitly, I'm thinking about the outcomes there. I just haven't written them, okay? And even more shorthand, I might just drop the curly brackets. As you use probability more and more, you'll see this thing on the bottom the most, but you have to remember that it's always coming from this probability measure on the sample space. But usually you don't need to access it at that level, but it's important to know that that's actually what's happened. Okay, so this is our definition for the PMF. And we're going to start using, as I said, this notation more frequently, right? So I'm just saying, okay, the probability measure applied to big X, but this is not an accurate statement. It's just a shorthand notation to avoid writing too much. And probabilities are really assigned to events, and those are subsets of the sample space, right? So they're not assigned directly to random variables, okay? But more or less, this distinction is important when you're kind of dealing with more subtle issues, and usually we can kind of brush over it when we're just doing, everyday calculations. All right, let's do some everyday calculations. So back to experiment 3. Remember, in experiment 3, I was rolling 2 4-sided dice, and let's say all the outcomes are equally likely because these are fair dice. And remember, in the experiment 3, I took x, the random variable, to be the sum of the rolls. Okay, so just to remind you, I'm going to write the sample space. So the sample space was the pairs ij, those were omega, and ij could take values in 1, 2, 3, 4. That's my set builder notation. X of omega was just I plus j, the sum of the rolls, and the range therefore was 2 up to 8. Okay, so that reminds us of experiment 3. So I want to work out the PMF. So that's what I'm going to do. I'm going to calculate the PMF for this experiment. So the first value I should try to get is the PMF at 2, right? So the PMF, the inputs come from the range. The first element in the range is 2. And so what I'm asking myself, if you go back to the definition on the previous slide, is to calculate the probability measure of the outcomes that are actually equal to 2 if I take their sum. And so the only outcome that has a sum of 2 is 1, 1. And that's what I'm trying to calculate the probability of. And that happens to be 1 over 16, because there are 16 possible rolls, 4 times 4, and this is just one of them. So I get 1 over 16. Okay, it'll get easier from here. So now I'm calculating the PMF for value 3. And so what can take the value 3? Well, if I have the outcomes, let's say 1 and 2 or 2 and 1 as my rolls, then the sum is 3. And there's 2 out of 16, so that's 1/8. So for 4, what do I have? I'm going to have the rolls 1, 3, 2, 2, and 3, 1. So there's 3 out of 16 there, right? And then for 5, that's going to be my highest value, right? Because I could be using 1, 4, or 2, 3, or 3, 2, or 4, 1 to get 4 out of the 16 outcomes. So it's 1/4 for the probability. So this is how I'm computing the PMF here. I'm basically looking into the sample space, picking up the outcomes that match this output for the random variable, and then I'm just working out their total probability. So I have, again, 6. So what's going to give me the value 6? It could be 2, 4, or 3, 3, or 4, 2. So I have 3 possibilities here out of 16. And then going back down to 7. So what's going to give me 7? I could have had, let's say, 3, 4, or flipping the order 4, 3. Those are the only 2 possibilities. So 2 out of 16 is an 1/8. And finally, for 8, the only way I can get that is by seeing 4, 4. So just 1 out of 16 possibilities. Okay, so I just worked out this PMF. It was a little bit tedious, but I could do it. It's, hopefully if you kind of stare at this for a while, it's clear what happened. And how can I represent this a little bit more concisely? Okay, so I want to have some useful ways of writing out a PMF without having to write this whole list. So one way I can do it is simple. I can just write it case by case for the different values it can take. So I can say, okay, I have a PMF, and the PMF can take the following values. So the lowest value you can take is going to be 1/16. That's going to happen when x is 2 or 8. It can also be an 1/8. That can happen when x is 3 or 7, or 3/16 when x is 4 or 6, or a 4th when x is 5. Okay, so that's a little more concise. I can also plot it, right? So I can do a stem plot. So here I'm going to draw the x-axis, and I'm going to label it 1 up to 8, right? So only 2 through 8 are going to be active, but just to show you the whole axis. And I'm going to draw gradations on the y-axis here, which is the PMF value. So remember that it took values from 1 over 16, 1/8, 3 over 16, and 1/4. And so what I'm going to see is an increasing plot starting at 2, going up to an 1/8 at 3, then 3/16, then a 4th, and going back down. So 3/16, an 1/8, and a 16th. So I've just taken these values and plotted them. And maybe this is sometimes an easier thing to look at. Or finally, I could also have a table. So sometimes it's easier to just have a lookup table here. So I'm going to draw, so the entries of the table are going to be either x, the value, or the PMF, plugging in for that x. So I have x from 2 to 8, and I'm just going to put in the values that I had up there. So this is just another way of writing this down. And sometimes the table helps me visualize what's going on. So I'm just transcribing the values in the PMF, and I get my table. Okay, so let's talk about some basic PMF properties. So these come from the basic probability axioms. One of them is just going to be non-negativity, so the PMF cannot be negative. The other one is normalization, so the PMF has to sum to 1 if I sum up over the range. And the last one is that if I pick up an event, which is a subset of the range, then the probability that x falls into that set B is something that we call P sub x of B, and I'll say more about that in a second, but it's really in our shorthand, the probability that x falls into B, which I just get by adding up all the x in B and summing up the PMF. And this is additivity. So I use this shorthand here, but what was I really talking about? So in green, I'm going to write that this was the probability measure of the outcomes in the sample space for which the mapping throws them into the set B, okay? And additivity lets me just write that as the sum of the PMF values. One thing that's a little bit new here is this probability measure with a sub x there. This is something that, it's a nice shorthand to have available sometimes. It just means that you could think about a probability measure built around the random variable rather than the original experiment. And this is a shorthand for that. But more or less, don't worry about it. I think that the convenient thing to kind of have, in in hand is the probability measure of the set X falling into B. Okay, so a little notation that I use here that maybe just to remind you is that summing up from X and B means add up the values of the PMF for every X that belongs to the set B. Okay, so as an example, let's say B is 1, 5, and 8. Then when I take this sum for X belongs to B, I'm adding up the PMF for 1 to the PMF for 5 to the PMF for 8. Okay, this is something maybe, just you've seen it around, but just to remind you. Okay, one more thing we're going to introduce here is the cumulative distribution function, or the CDF. Okay, so what's the definition? So the cumulative distribution function, all right, what it does is it accumulates probability, and it takes as an input a real number, X, and it's going to return the probability that the random variable X is less than or equal to X. So it's capturing all the probability up to and including that X. Okay, so the notation for this is a capital F with a subscript, big X, and a random, like kind of the little value X. And what it is the probability measure applied to the outcomes that map to a value less than or equal to little x. Okay, so shorthand for that, I just write the set of random variable that's less than or equal to this value, and I can drop the curly brackets. Again, these are just convenient to have in hand, but they're not capturing the underlying reality. Okay, why do I want this? It turns out it's not very useful for discrete random variables. It's important to define it though, because as we go ahead and we start building up continuous random variables, so as we start thinking about other things, this is going to be what links the two together. So there are things that we're going to be introducing now, like the PMF, that will not apply to continuous random variables, but this CDF will apply, and we will need to think about it. So it's important to kind of understand it now while things are a little bit easier. Okay, what are the properties of the CDF, just to have it defined? Well, so we're just going to do some of the obvious ones. Let's say I put in minus infinity into this function, meaning, by the way, that what I'm doing is taking the limit as x goes to minus infinity, then I get 0, meaning that there's no probability of being less than minus infinity. By that same token, so if I plug in infinity, meaning I take the limit as x goes to infinity, then I get 1, and this is basically normalization. So the total probability, which is what happens if you're less than or equal to infinity, which is everything, the total probability of everything is 1. We also know that this CDF will be a non-decreasing function of x, and that's due to non-negativity, because if it went down, that meant that there was some negative probability pushing it down. We also have that if I'm interested in calculating the probability of an interval, I can just take the difference in CDF values. So the probability that x falls into this half-open interval, so starting at A not inclusive, but going all the way to B including B, is this difference of CDFs. I also have some kind of continuity from the right, so if I take epsilon down to 0 from the right, so I'm just bringing it down, then I have that f of x plus epsilon is equal to f of x. So I'm kind of rushing through these a bit, and again, it's because we're not going to be really using this directly in discrete random variables. The main thing to notice is what this object is going to look like visually. It's going to be a piecewise constant function, and what it's going to do is jump up by the value of the PMF at every point x in the range of the random variable. So at every point where the PMF is actually positive, it's going to jump up, and otherwise it's going to stay flat. And let's just go through an example so we can just visualize that. Okay, so in my example, I'm just going to draw a plot for you. So here I'm plotting a PMF. Okay, so here's my PMF. So I'm going to label the axes, and I'm just going to have, let's say, it can take values. Let's go with a fourth. Okay, and let's say a half. Okay, so those are going to be my PMF values, and let's say the probability of being 1 is a fourth, the probability of being 2 is a half, and the probability of being 3 is a fourth, so that sums up to 1. And now let's work out the CDF. Okay, so remember, so the PMF is the probability that the random variable is exactly equal to some value. The CDF, which we're about to draw, is the probability that it's less than or equal to that value. Okay, so what's going to happen is, so to start out, so let's label the axes first. So to start out, what's going to happen is I'm going to come in from the left, and I'm going to always start at 0. So I'm coming in from minus infinity, starting at 0, and that's what's happening here. So I'm coming in, and I come up to 1, And now what's going to happen is, as I said, I'm going to jump up by the value of the PMF. In this case, I'm going to jump up by a fourth, okay? Because it's the probability that I'm less than or equal to a value, and the PMF value at 1 is a fourth, meaning that the probability that you're equal to 1 is a fourth. So I need to now jump up to catch that. Then I'm going to slide along until I get to 2, because there's nothing new until 2. And once I've hit 2, I'm now accumulating probability. So I'm going to jump up by a half, which is the value of the PMF at 2. Okay, so then I go up to 3/4. And then I'm going to finally slide along. And I'm going to go all the way to 3. And I'm going to jump up by the value of 3, which is a fourth. Okay, and then I'm going to go on forever. The reason I go on forever is I've hit 1. Once I hit 1, then I'm done, because I've captured all the probability, and then I just go on to infinity holding the value 1. Okay, so just to kind of solidify this, let's do one more example. So I'm going to draw a different PMF. This last one that I drew was kind of symmetric. So this one I'm going to draw as a little less symmetric, but it's kind of the same thing, right? So same kind of idea. So I'm going to label the x-axis 1, 2, 3, 4. And maybe in this case, the values I'll take are a fifth and 2/5. So I'm going to have the value. So I'm going to write out the PMF. So let's just say that at 1, I'm 2/5. At 2, I'm 0. At 3, I'm a fifth. And at 4, I'm 2/5. So it sums up to 1. And that's it. And by the way, I mean, here we've just been doing simple examples and, things have been integer valued, but there's no reason to have discrete random variables that take integer values. They could take fractional values or whatever you like. As long as there's a countable number of them, it's fine. So here's the CDF, which is going to start at 0 from the left and then come along until it hits the first positive value, which is going to happen when x is equal to 1. Then it's going to jump up by the value of 1, so it jumps up by 2/5, because it's the probability that the random variable is less than or equal to x. So once it hits 1, it has to catch the probability of x. Now I go along all the way to 3. I've skipped over 2 because 2 has probability 0, so there's no jump at 2. At 3, I jump up by the probability of being exactly 3, so that's a fifth. And then I'm going to slide along till I get 4, which is going to give me the remaining probability, right? So that's the last part of the probability, which is 2/5. I jump up by 2/5, and I go along again forever because I've captured all the probability, which is 1, and I just go along forever to infinity. Okay, so this is a visual way of how to think about and draw CDFs. And that is it for our introduction to discrete random variables.